we will continue our discussion on forces on bodies, and towards the later part of today's lecture we will also see how to solve problems, and we will look at one of the basic steps which is needed in all mechanics problems to solve problems, and that is called the free body diagram. So, let us start. In the last class we ended with laws of friction, and we talked of solid friction or friction between two solid bodies, and we showed that friction force was proportional to the normal reaction if the bodies are slipping or impending slip is there, and we had a detailed discussion about this. Now, let us just have a look at what happens if the contact of a solid body is with a fluid, and by fluid I mean a liquid or a gas. So, for example, let us say this is a block which is moving let us say with a velocity v, and surrounding this is air or water. In fact, we could think of this as an aeroplane which is moving. So, now the surrounding liquid applies a tangential force on the solid, and the typical term which we use is for the fluid friction, we call it as a drag force. Now, there is no reason that the fluid should exert a force only in the opposing the direction of velocity. The fluid could also exert a force in a direction perpendicular to the velocity, and that force we will normally call that as the buoyancy force or a vertical force, sometimes it is also called the lift force. But when we talk of friction, friction caused by the fluid is in a direction which opposes the velocity, and what we empirically observe from experiments, what we observe is that this drag force is a function of velocity. Now, notice the difference between solid friction and fluid friction. In the solid friction, if the body was moving, the friction force was related to the normal force, but in case of a fluid friction, the drag force is a function of the velocity of the body, and this drag force is proportional to velocity if the speeds are very low. Sometimes when we talk of this for a sphere, this is called Stokes' law of viscosity, and if the speeds are relatively higher, the drag force is proportional to the square of the velocity, and it could also be a function of v to the power of n, where n could be between 1 and 2. Therefore, in a general way we can say that the drag force is a function of velocity. So, fluid friction, when we talk of friction due to fluid on a solid body, this depends on velocity, and it opposes the motion of the body. Now, in some cases it is possible that the fluid helps the body to move forward, then the terminology we use there is thrust instead of drag, but those cases are you will probably come across them in detailed later advanced courses of fluids. Now, from here what we realize is, if we look at the forces which act on the body, we will look at some more forces, but these forces I will just bring this in discussion right now, since we have talked. They could either, so external force on a body They could either be constant, they could be a function of distance, and this we saw in electrostatic forces, gravity, we saw all these were function of 1 over r square. So, it is a function of distance, or the external forces could also be a function of velocity, as we saw in the force due to fluid friction, or sometimes these forces could be a function of time. And in each of these cases, the way we will solve the problems will depend on how these forces are acting, because eventually finally what we will put is that sum of external forces on the body is equal to mass times acceleration. So, this is Newton's law, but now the way we attack the problem will depend on if the force is constant, a function of distance, a function of velocity, or a function of time. And these details we will see as we come to different type of forces. And what we will also realize is a constant force, if we develop special techniques for when the force is a function of distance, velocity, or time, then the constant force could be used in all these techniques. So, and this we will show. For example, you have seen, we have talked of impulse, and we defined impulse as integral of f times multiplication of force times time. So, when force will be a function of time, then possibly impulse methods will be the ones which we will use. What we will also see is when force is a function of velocity, then we will write this acceleration as dv by dt or v dv by ds, and then split the two parts. When force is a function of distance, then as we will see in the next chapter, we will develop work energy methods for solving the problem, and they often offer a convenient way of solving the problem when force is a function of distance. And when force is constant, we could use either the work energy method or the impulse method to solve the problem. But before we talk of these different methods, let us continue our discussion on contact forces. We had talked of contact forces on a solid, on a body, and we first said that if two bodies are in contact, let us just sum that discussion up. If two bodies are in contact, then, so let us say this is body A, this is in contact with body B, then on body A, the body B exerts a reaction force, we called it force on A due to B, and we show it with a general direction. Now, what we have also shown is that if these bodies are in contact, then FAB we divide into two parts, a normal reaction and a friction force. The generalized version of friction force would be a tangential force, and we find in most cases it is just the friction force. So, this is the contact force, we divide that into two parts. Now, we have some special type of contact forces in addition to the bodies touching each other. And there are two special types which I would like to discuss. The first one is, suppose we have a block or a particle and this is tied to a string, and the string is pulling the body. So, this is body A, this is a string, and the string is pulling the body. Now, in this case, the string exerts a force on the body in the direction of the string, and what we have is, this is a block and this is a string. The force which the string exerts on the body we call this force as tension, and the string pulls the body with the force T, and we give a special name to this as tension. Now, here what you will realize is that if first thing is, let us just see that this tension is in the direction of the string. Secondly, what we realize is, if we have this block and if there is a string like this, but if I compress the string, then the string will just fold and it will not exert any force on the body. So, this is very clear, we have seen this. If you have a body like this, you tie it to a string. So, let us say if this is a string, if there is a body, I pull it with a string, then a force is exerted on the body. But if the body is lying like this and I push the string, then the string will just crumple, it folds up and it cannot exert any force. So, therefore, whenever we have strings, we show the force due to the string on the body. So, if this is the string like this, and if this is a body, string is tied like this, this force is what we call as a tension on the string. And in case what we can have, what we often have is problems like this where we have, so let me show the string with a different color. So, we have a string which ties two bodies. Now, here if we make two assumptions. One is, if we say that the string is light, which means its mass is nearly equal to 0. And secondly, if the string length does not change. So, length of the string stays constant when we apply force on the string, or as a reaction the string will apply force on the body. So, now here let me call this M1, let me call this M2, so that there is no confusion. And what we will say is that, so now here when we look at it, when we look at this body M1, its weight W1, which is equal to M1g, acts down, and the string offers a force on this which we call as tension, let us call it T1. Now, what will happen is, if the string is light and if its length does not change, then what we find is, as we traverse along the length of the string, the tension T, the magnitude does not change. And this is because when the string is light, then even if we look at mass times acceleration, that will be nearly equal to 0. So, therefore, there will be no force which will be provided internally by the string. So, therefore, the tension in each of these parts of an inextensible string of which is light is the same tension T1 which goes on. Now, when I look at this mass M2, and if I look at its show the forces on the mass M2, then I will have its weight W2 going down, and I will have a tension, let me first call it T2, but because of what I have said, T1 will be equal to T2. So, it is the same tension which goes through the string. And now, in problems like this, you will also have to realize, we will be solving many of these, but if there is a single string tying these and if this is inextensible, then the acceleration of bodies 1 and 2, they will move by the same length. If suppose body 1 is heavier, this whole thing is moving down, then this will move down, but if this moves down by a distance x, body 2 will move up by a distance x. So, therefore, the magnitudes of acceleration of bodies 1 and 2 will be identical. And these sort of constraints you will have to work out when you solve the problems. We will look at more details of these in specific cases, but I am just pointing these out to you. So, therefore, this is how we show the forces due to a string on bodies. So, let us look at the second type of contact force by special bodies called spring. Springs you may have seen, if you open up a ballpoint pen, you see a small spring. So, this is like a coiled wire. Now, if you realize what we do is, in a spring, if I extend the spring, so if this is the spring and you pull it, then you find a force is needed to pull the spring. And not only can you pull it, we can also compress the spring, which means we make the same spring and we compress it, and in this case also a force is needed to compress the spring. So, if this now spring is tied to some body, so then since a force is needed to compress the spring will put an opposite force on the body. So, if a body is connected to a compressed spring or to an extended spring, then a force, equal and opposite force will be applied by the spring on the body. So, a spring is something which we can say that, let me just give you the definition of a spring. So, spring can be compressed or extended by an external force, and it generates a restoring force, which is what we are calling as the reaction, which it applies on the body of contact. And force on a spring, what we find is, this depends on the amount of compression or extension. To compress the same spring by a bigger amount, so that if you want to make it smaller, you will have to apply a larger force. And one of the ways how we mathematically write springs, all springs may not behave like this, but a lot of springs we have this relation that the force in the spring is equal to minus k times x, where x is the change in length of the spring as compared to, or with respect to its unstretched length. An unstretched spring, we do not, for an unstretched spring x will be 0, there will be no force required. The minus sign tells us that, indicates that force is opposite to the direction of displacement. Now, this term k, this we call the spring constant, and as we said, in a lot of springs we can assume that k is constant for that type of spring. The units of k, this will be equal to, in SI units, k will be obviously newtons per meter, force per unit length. So, that will be the units of k. So, this is how if we have a spring which is connected, we write the expansion of forced because of the spring which it will exert will be minus k times x. So, now this is another case where the force is a function of the displacement of the body. Okay. So, now we have seen different type of forces which act on a body. Now, how do we go about solving a mechanics problem? So, now in a typical problem what will happen is, so let us now come to problem solving using laws of mechanics. And what we have is essentially we will be using Newton's second law as the governing principle, and that is sum of the external forces on the particle will be equal to its mass times acceleration. Now, this is a vector equation, we will write it in the general form like this. Now, what will happen in the problem will be that either the acceleration or one of the forces which are acting on the problem will be unknown, and by applying this equation we will be able to get that unknown. So, and now because this is a vector equation, if we talk of two dimensional situations, that means we can write it in the so this is vector equation, and for 2D we will have two components, the x component and the y component. So, that means in a problem we will have two unknowns. Now, the unknown could be either a force or an acceleration, but also we realize when we solve problems like this, for example, there is a force of friction which comes, then we may have to use the other relations which we know. If the body is slipping, then force of friction we know is equal to mu k times n. So, therefore, friction is related to the normal reaction. So, that will come in as a third equation in addition to the two components of Newton's law in x and y direction. So, we may have to use the third equation, F is equal to mu n. In some cases F is equal to mu n will not be used if it is a case of no slip, and then we will have only two equations and two unknowns. So, now what we do is when we solve the problem, the first step is what we call as drawing a free body diagram of the system. I am using the word system so that we can generalize it later. In current context, we will be drawing free body diagram of the single body in which we are interested. Sometimes there may be two bodies. Let us first talk of free body diagram of a single body. What do we mean by a free body diagram? So, what we do is we first talk of a single body. So, we isolate the body in question, and then we show a notional diagram of the body, and if we are not interested in rotation, we are talking of the body, then this will be treated as a particle, then we can even show it as a point. And there what we do is we show all external forces acting on the body, and this is what is a free body diagram. So, let us say, let us take a very simple case. There is ground on which I have been taking this example again and again. A block is kept on the ground, and here we want to now draw. This block is at rest, it is just kept on the ground. So, it is the case as we saw yesterday of, let us say, this pen which is, let it come to rest. So, this is lying on the ground. I want to draw the free body diagram of the pen. So, here I am just replacing it by the block. So, first what I will do is I will show the block. Now, notice in the free body diagram the ground will not come in. When I say free body diagram of the block, only the block comes, and then what I do is I show all the external forces. Now, when I show the external forces, there are two types of external forces. One are forces acting from a distance. So, on this block, which force is acting from a distance? And what we find is the only force which acts from the distance is gravity, and this will be the force due to that will be represented by its weight. So, the first force we show on the body on this block is its weight W, and sometimes if we want, either we can show it as W or we can write it as mg, where m is the mass of the block, and we may have to use W is equal to mg in the problem. Now, so this is forces acting at a distance. Secondly, we will look at the contact forces. So, now for the contact forces, let us show, this was our problem, this is the block, we have to draw the free body diagram of this. So, and what we have done is we have isolated the block. So, first step is isolation of the body, we show forces at a distance, we show the force W. Now, what we should do is, in a general problem, mentally make a trip, just go all around the block where the block is in contact with anything else or not. And what we find is, this block is in contact with the ground at the bottom. At this place, the block is in contact with the ground. So, now we have to show the effect of ground on the block, and the effect of ground, as we said, in general would be a normal force and a friction force. So, therefore, we show the normal force and the friction force. Maybe you could have also shown this as W and a single reaction force at an unknown angle. Actually, this is the way we should show it, but then we know we resolve this reaction into a normal component and friction. So, we show it as N and F, and as of now we do, the block is not moving. So, this is the free body diagram of the block. Actually, the free body diagram of the block is W and a reaction force at some arbitrary angle phi, we do not know what phi is, or we could show it as W and N and F. So, this is the free body diagram of the block. Now, let us make it slightly more, let us add things to this. Suppose this is the block lying on the ground, and there is a string which is tied to this, which is at an angle theta, which is constant, and the string is pulling the block with a force T, which we call the tension T. And now, this block has a mass m, and we are supposed to draw the free body diagram of the block now. So, now when I draw the free body diagram of the block, first again I only show the block. Showing the block and the ground in the free body diagram is incorrect. Only that body has to be shown on which the forces are acting, or which you want to analyze, and then we show the weight W, we have a normal reaction, we show a friction force. Now, in this case we will have to analyze, but friction force could be in a tangential direction, it could be forward or backward. When we once draw, we just show it as F, and then we will analyze and get the direction of the friction force, and then also we have the tension T. And if we treat this block as a particle, what we could do is, instead of showing this as a full block, we could have just shown this free body diagram treating this as a particle. So, therefore, we will have the weight W, there is a normal reaction, there is a friction force, and there is a tension T, which is at an angle theta. So, this is the free body diagram of the block on the ground with a string attached. All the forces are to be shown. Now, you may ask the question, what about the accelerations? Well, we will show all the forces, and then when we solve the problem, then we will say sum of all the forces must be equal to mass times the acceleration. So, in a free body diagram, we only show the forces and then we analyze the free body diagram to get the solution of the problem by putting F is equal to ma, and we will just see that. Now, typically once we have these, at least for your level, you will have two dimensional problems. So, one thing which you should do is, because if the problem is 2D or even if it is 1D, in 1D you will have only one direction, in 2D there will be two directions. So, we should show x and y axes on the problem, on the free body diagram. So, somewhere next to the free body diagram, for example, I had drawn the free body diagram, normal reaction W, friction force T, I should show my x and y coordinates on the problem. The reason is because eventually I will have to do a vector balance. I will have sum of forces in the x direction is equal to mass times acceleration in the x direction. Now, if you have shown x like this, then anything which is in the opposite direction will come with a minus sign. So, therefore, drawing the directions is very important. That is one thing. And secondly, x and y need not be along horizontal or vertical. They can be along an incline or at an angle. Only thing we have to ensure is that x and y have to be perpendicular. But other than, so for example, if we have a problem of a block lying on an inclined plane which is at an angle theta from the horizontal. So, we could choose, for example, x like this, y like this. So, only thing we require is that they have to be mutually perpendicular. Other than that, and maybe I can choose x like this, y like this, even that would work. All I have to ensure is that I make perpendicular axes. So, these angles have to be 90 degrees, otherwise I can choose x and y as any two perpendicular directions along any orientations. And then we will stick to whatever is along the positive x, what we have chosen will be positive, whatever is along the negative x or negative y will be negative. So, this is what we do. Then let us now, so after we draw the free body diagram, so we will draw the free body diagram, show all the forces on the body, and then we will put F is equal to ma. So, in a two dimensional problem, we will resolve F along x and y. Now, this F is a sum of all the forces acting on the body. So, for example, let us go back to this block, to this problem. We have drawn the free body diagram here of the block. There is this normal N, there is W which is equal to mg, there is a force of friction, there is tension, and in this problem suppose we choose x and y like this. So, now when I apply Newton's law to this body, so I will put sum of forces in the x direction is equal to mass times acceleration in the x direction, sum of forces in the y direction is equal to mass times acceleration in the y direction. Now, so here now when we look at the left hand side comes from the free body diagram. The right hand side will be the kinematics of the problem which we will analyze. So, for example, we are talking of a block which is tied with a string, and this is on the ground like this, and we want to find its motion. So, let us say suppose the tension T is given and we want to find the acceleration of the block. So, if T is given and we want to find acceleration of the block. So, here what we will do is we draw the free body diagram. So, that means it is given to us in this problem that the block accelerates to the right with acceleration a, and we want to find this. So, now when we draw the free body diagram, we have drawn this again and again. We have T, we have N, we have W, and we have the force of friction. Let us solve this problem. Now, when we start counting the number of unknowns, so the normal reaction is not known, this is one unknown. The friction force is the other unknown, number 2. The tension T is given to us, acceleration is unknown number 3. So, that means we have 3 unknowns in this problem and we have to solve one of them, that is the acceleration. So, after we draw the free body diagram, let us then we write forces in the x direction. So, this is x, this is y. So, forces in the x direction, if this angle is theta, then we have, because of this tension T, the force in the x direction will be T cos theta. So, it is T cos theta minus F is equal to m times A. This left hand side comes from the free body diagram, T cos theta minus F, and this is equal to mass times acceleration of the block. Then we also go to forces in the y direction. So, what we will get is N plus T sin theta minus W is equal to mass times, in fact let us call it as MAX, and MAX is equal to MA. This is equal to mass times acceleration in the y direction, and we know that this block is moving only along the x direction. So, therefore, this acceleration is equal to 0. So, what we get is N plus T sin theta is equal to W, which we can also write as mg. So, this gives us the second equation. We need a third equation again, and the third equation which we will get will come from the force of friction. Now, here we know this is a case of the block is slipping on the ground, and in fact that is why, because it is slipping in the forward direction, so therefore friction was shown as acting in the backward direction, which is the correct direction, and because the block is slipping, friction will be equal to mu k times n. So, friction is equal to mu k times n. This gives us the third relation, and now we can solve the 3 equations and 3 unknowns, and we can get the value of acceleration. If we want to actually do this, so what we have is n is equal to, let me work it out, n is equal to mg minus T sin theta. Mass of the block is given to us, so therefore we know the normal reaction now, and from there what we get is friction is equal to mu k times n. So, is equal to mu k times mg minus T sin theta, and then what we get is m times A is equal to T cos theta minus F. So, that will be equal to T cos theta minus mu k times mg minus T sin theta. We know the values of mu k will be given to us, mass of the block is given, tension is given, the angle theta is given. So, from here we can get the value of A. So, this is how one uses a free body diagram to solve the problems. Once again, the basic equations to be used are sum of forces in the x direction is equal to mass times acceleration in the x direction, sum of forces in the y direction is equal to mass times acceleration in the y direction, and in addition we may have to use friction force is equal to mu k n or mu s n to solve the problem. But if the bodies are not slipping, this is only in case of slip or impending slip. In case of no slip, friction will be an unknown like other forces and will not be able to solve for friction directly. It will come from the solution of the equations. Let us come back to the example of the block lying on a table. So, now we drew the free body diagram of the block. We showed the block like this, or maybe we show it as a particle, and then we have the weight, the normal reaction and the friction force. Now, if the block is at rest, that means there is no slip, it is just moving. So, acceleration of the block is equal to 0. Now, here when we apply sigma f x is equal to 0, because acceleration is 0, and sigma f y is equal to 0. So, this gives us n is equal to w, and this one gives us friction force is equal to 0. Sorry, the other way around, f y will give you this, f x will give you friction force is equal to 0. So, in this case there is no friction force acting on the block. Now, let us consider a case when the block is on the table and the table accelerates with an acceleration a in the right direction and the block is not slipping on the table. So, in this case we would like to know if the acceleration a is given, what is the friction force acting on the block. So, acceleration a is given and we want to know what is the friction force on the block. So, what we do is again we draw a free body diagram of the block, and which I show as a particle. I will have its weight, normal reaction, and then as usual I show the friction force like this. So, I have drawn the free body diagram. This is a case of block not slipping. Since everything is moving to the right, I show the friction force on the block as in the left direction. So, this is my free body diagram N W F, and then I put sigma F y is equal to 0. There is no acceleration of the block is equal to a in the I direction, because it is moving to the right with an acceleration a, it is not slipping on the surface of the table. So, sigma f y is equal to 0 gives me n is equal to w, and when I put sigma f x is equal to m times a, this gives me minus f is equal to m a. Now, we know a is positive, so it gives us f is equal to minus m a, which means that friction is in the right direction. So, therefore, the correct free body diagram finally turns out to be this, and friction force on the block is acting in the forward direction, and this is equal to m times a. So, this is the friction force acting on the block and it acts in the forward direction. Somehow intuitively we always feel that if the block is moving in the forward direction from a ground frame of reference, friction on this should be acting in the backward direction. But actually here it is the friction force which is providing the acceleration to the block in the x direction. And now, is it counterintuitive? Let us try to think about this. The block was at a state of rest when the table started to move. Now, the table has suddenly started moving, the block is not slipping. So, now something has to provide an acceleration to the block in the positive x direction, and that something is nothing but the contact force which it has with the table, and whose tangential component is nothing but the friction force. So, therefore, the friction force on the block is acting in the forward direction. Another way to look at it is that the inertia of the block tends to hold it on the table. That means, the block tends to stick on the table, but it is forced to move forward. So, therefore, the relative motion of the block with respect to the table will be in the minus I direction, and so a friction force has to oppose this. So, it will be in the plus I direction. So, now if you have to find the maximum value of acceleration for which the block will not slip. So, if you have to find the maximum value of A for which block does not slip on the table. So, then clearly we know till the block starts to slip, f is equal to ma. Now, the maximum value of f before which slip takes place will be equal to mu s times n, and this must be equal to ma, and n from the balance of forces in the y direction turns out to be equal to w. So, mu s times w is equal to ma, and w can be written as mg. So, therefore, what we will get is, if we put this in, we will get the value of mu s is equal to A by g. And so, if so A at which slip takes place will be equal to mu s times g. And if the acceleration exceeds this value of mu s times g, that means the block will start to slip. So, if acceleration exceeds mu s g, the block slips, and then once the block slips, what we will have is the free body diagram. We will have n, we will have w, we will have friction, and this will be equal to mu k times n, and this will become mu k times mg, and then we can apply the relations. N is equal to w has already been used, and the forward acceleration of the block m times a will be equal to f. So, now the block is slipping. This value of acceleration, this is acceleration of the block in the ground frame. So, therefore, this acceleration A will be equal to acceleration of the table minus acceleration of the block with respect to table. So, we will get m times A minus acceleration of the block with respect to table is equal to mu k times mg, and from here we can work out the value of acceleration of the block with respect to table. So, m a minus m, so m will cancel out from all these. So, what we will get is acceleration minus mu k times g will be equal to acceleration of the block with respect to the table, and this will be of course in the minus I direction. So, this is how we can work these problems. A similar example comes, and this is often used to find how do we work out the value of mu s. And let us look at it. Suppose we have a block or a coin kept on an inclined plane, and the angle is theta. What we do is we initially keep theta is equal to 0 degrees and we raise the value of theta. So, we initially the block would be at an horizontal level and slowly we raise the angle of the incline, and what we find is at an angle theta s, let us call it, the block starts to slip. So, what we want to find is find the friction force when theta is less than theta slip, when theta is equal to theta slip. So, let us do the analysis of the problem for all these three cases. Now, when a problem like this is given and we ask you to find the friction force, one of the most common errors we encounter is students writing that friction is equal to mu times n. They will use either the value of mu s or mu k, and this clearly is incorrect, because if we are in the range when theta is less than theta s, then friction force we cannot relate it to normal reaction except by saying friction has to be less than mu s times n. So, block is here, it is kept at an incline, this is the angle theta. Let us draw. So, let us look at the first case when theta is less than theta slip, and let us draw the free body diagram of the block. So, this is, we represent the block by a point, and in this example, because we have things at an incline, we can choose x axis like this, let us choose y axis like this. So, we are choosing, and we realize this x axis, this angle is theta. So, when I draw the free body diagram, what I have is the weight W, which is acting vertically down, and then we will have a normal reaction, and because this is tending to slip down, the friction force we show as up. We will analyze the case as it turns out to be. So, that means these are the forces which are acting on the particle, a vertical downward force mg, normal reaction n perpendicular to the block. So, this is the direction of n, this is the direction of F along the block, and these are the forces. Now, in this particular case, and this we should learn very fast how to do these things, that if this is at an angle theta with the horizontal, then what we find is that the component of W along this, if so, this is W and this makes an angle theta with the y axis, because x was making an angle theta along with the direction x makes an angle theta with the horizontal. W is vertical, so it will make an angle theta with the direction which is perpendicular to the given x. And so, if this is W, then we can resolve W as W cos theta and W sin theta like this. So, along the x direction, the component of W will be W sin theta, and along the y direction the magnitude is W cos theta. So, if I once again, this is my incline, I draw the free body diagram of the block. What I can do is I can write this as W cos theta, W sin theta, I have done this, and then we have the normal reaction and we have the friction. So, now when theta is less than theta s, block is at rest. So, in this case n is equal to W cos theta and F is equal to W sin theta, because Ax and Ay are 0. So, we have this relation. So, friction force in this example, when the body is not slipping, is just at rest, is equal to W sin theta, okay, and the normal reaction is W cos theta. Now, this free body diagram is valid for all theta. So, this free, let us write this, this is valid for all theta. What is going to change will be when theta is equal to theta s, then friction force will become equal to mu s times n, which will become equal to mu s times w cos theta, and this must be equal to w sin theta. So, therefore, what we get is mu s is equal to sin theta upon cos theta, which is equal to tan theta. And this is how one determines the coefficient of static friction in cases like this, that you slowly increase the inclination of the block and the angle at which the body which is lying on the incline starts to slip, that gives you the coefficient of friction between these two bodies, that is tangent of that angle gives you the coefficient of friction. And to measure tangent, either you can measure the angle or you can look at the x distance and the y distance and take a ratio of y distance to x distance, that will give you the angle theta. And what happens if theta is greater than theta s? If theta is larger than theta s, then the block accelerates down with the incline with acceleration a, and now this acceleration becomes an unknown. The free body diagram stays the same as we have done n f, but now this f becomes equal to mu k times n w cos theta w sin theta. So, we will get n is equal to w cos theta w sin theta minus mu k times w cos theta is equal to m times a, and this w is nothing but m times g, and you can use this to find the acceleration of the block. So, with this we have seen simple systems, how to draw free body diagrams and how to solve problems. In the next class we will continue, we will look at more system of two bodies or multiple bodies and also circular motion.